everything where it needs to be before we start. All right, let's begin. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Office of Public Outreach, and it is my pleasure to be your host each and every month. If you came in, you hopefully grabbed a lithograph over here. This lithograph has special meaning. It will actually be used as part of the talk tonight, okay? So the lithograph on supernova remnant SN 1006. And if you want to know what that means, you look over on the back and you can see all this wonderful text here that we've written, as well as a context picture of the full supernova remnant, and that will also appear in tonight's talk. All right, so make sure you silence your electronics. The modern age requires that we have things, ringtones, text notifications, and camera clicks turned off. Thank you very much. Tonight, the Crab Nebula and things that go kaboom in the night by, this guy. Okay. Upcoming, March 3rd, we have Nestor Espinosa talking about exoplanets, a search for new worlds. Exoplanets are just massively hot. I was recently informed that Hubble is actually spending on order 10 to 20% of its time looking at exoplanets and exoplanet atmospheres and things these days, which is kind of cool because Hubble was never designed to look at exoplanets. We didn't know about exoplanets until 3 or 4 years after Hubble launched. And that shows you how we can just adapt this wonderful telescope to look at anything in the universe. April 7th, we will be celebrating the 30th anniversary of Hubble with an all-star cast, which means nobody's willing to commit exactly who's going to talk on April. But there will be probably more than one speaker. And in May, we have our perennial favorite TBA who will show up. I actually filled the June slot today. I still have to fill the May slot. Reminder, for those of you who are here, you know about this. The building is the lobby is under reconstruction. And February and March, they've told me, definitely will be impacted. There's still a question as to whether it will be done by the April public lecture, okay? So most likely, they originally expected to be done by April, but things can always slip, okay? Schedules can always slip with construction, all right? Using the alternate entrance, the signs were posted. The signs were easy to follow tonight. Okay, good. All right. And especially if you need wheelchair access, we can arrange it, but we need to have advance notice for that. All right. Website. If you just go to stsci.edu/public-lectures, you'll find our public lecture series website. Here is our webcasts, both on our webcast archives from STSCI and a playlist on YouTube, okay? The playlist on YouTube goes back like 5, 6, 7 years, maybe even 8 years. And the webcast archive goes all the way back to 2005. So we're approaching 15 years of webcasts on there. You want to binge watch? Yeah, you got a lot to binge watch, okay? Because each episode is at least an hour, sometimes an hour and a half. So good luck with that. Email, if you want to sign up for our monthly emails telling you about the lectures, fill out there, hit the subscribe button. Also on the web, we have the list of the upcoming lectures, and for each lecture, when you hit that Read More button, you will find the description of it, of the speaker, and after the lecture has gone, you will find links to the STSCI webcast here, as well as the YouTube webcast down here, okay? All righty, the email. As I said, you can sign up at the website. Some people don't like to do that. They write it on a piece of paper and hand it to me. That's just fine too, okay? We promise you will not get any spam. There hasn't been any yet, and we've been doing it for like 5 years. Comments and questions can go to publiclecture@stsci.edu. If you'd like to follow us on social media, the Hubble Space Telescope, the James Webb Space Telescope, and the Space Telescope Science Institute have 3 separate accounts on Facebook, Twitter, YouTube, and Instagram. So you can follow us. Maybe there's some more, but I'm not terribly social media friendly. I do some of it on Facebook and Twitter. You can follow me at Dr. Frank Summers. Oftentimes, after the lecture, we go to the observatory, the Maryland Space Grant Observatory. They informed me that the weather forecast did not look good, so that will not happen tonight. But they have open houses on Friday evenings. If you go over to their website, which is md.spacegrant.org, you can find this page about their open houses, and right there, that's the observatory status. On Fridays, it will be updated as to whether they are having an open house that evening, okay? All right, and now, news from the universe for February 2020. Our first story tonight, Goldilocks stars, looking for life in all the right places. All right, so we have had a new history of these extrasolar planets, which I mentioned earlier that, Hubble wasn't designed to look at extrasolar planets, but it's actually doing a good amount of extrasolar planet science now. So this is the plot of all the stars in the sky, right, ascension and declination here, that we knew of in 1987 that had planets. And you can see that's 0, all right? Let's put this plot in motion, okay? As the dates change, you'll slowly start to see a few of them in the early 90s. And the later 90s, it gets more, and into the 2000s, it becomes a lot more. And at the end 2010, you start getting the Kepler group in there, and you get a ton of planets, okay? So now we know of over 4,000 extrasolar planets out there, okay? We've gone from 9 planets to 8 planets to 4,000 planets, okay? So those of you who are worried about Pluto being out of a planet, no, we got so many more. Who cares about that, okay? All right, so, but the point is that it's now become a serious piece of science that we're doing. It's not just finding them, but it's also finding them efficiently and finding the ones we really want. So when you look at this star field here, you've got the red stars, the orange stars, and the white stars, and the blue stars, etc. Where are you going to look, okay? What is most likely to have planets? And furthermore, because this is what excites the public imagination and what, hey, we as astronomers also want to know, which ones are most likely to have life, okay? So what are the arguments you're going to have, right? Well, the star has to live long enough, okay? So all the short-lived stars, the white and the blue stars, they don't live long enough for life to develop, because life in our solar system took 4 billion years to become complex. The Cambrian explosion was about 500 million years ago, 600 million years ago, and we've been around for 4.6 billion years. So that means 4 billion years for life to develop. You need a long-lived star, okay? You also need a planet in a habitable zone that's going to be safe. And there can't be too much radiation and other things. So, using Hubble, they were able to go in and study a bunch of the stars and try and understand this high-energy radiation, using Hubble's capability for ultraviolet observation to understand the high-energy radiation factor in all of this. And this is the diagram they gave us here. So, if we start with the M stars, the tiniest stars, the red dwarf stars, okay? They have, because they're faint, they have a very small habitable zone. What really makes them not so great is that they have a lot of X-ray irradiance. They have, these small stars have a lot of stellar flares. They're very active, okay? And so even though there are a ton of them, they are the most numerous stars in the universe. About 74% of the stars in the universe are these red dwarfs. They are not really good for life because of all this X-ray irradiance, okay? If you move up to the K stars, it's depicted here as orange stars. They have a bigger habitable zone. They have some X-ray irradiance, etc., from this study. Not too much, but some to be worrisome. They're much less than the red, but 3 times more than the yellow. And they live for 40 billion years, okay? That's pretty good. If you go to the sun-like stars, the G stars, they have a much bigger habitable zone. They have a very acceptable X-ray irradiance because, hey, life developed here, but their number is considerably fewer. And living for 10 billion years, you're starting to get to the borderline of, well, could life develop? So the conclusion of their study was that the optimal stars to look at, if you're trying to find places where life could develop, would be those K stars. All right, the sun-like stars, just not as many as of them, whereas the K stars, the orange stars, would be more favorable. And this will help us design future searches that are looking for those type of planets. So we have to do these observations and this theoretical work to help design future surveys and make them as efficient as possible. Our second story, so long and thanks for all the PAHs. Now, you may not get this reference, okay? But this is a reference to the title of a book by Douglas Adams called So Long and Thanks for All the Fish. It's from the Hitchhiker's Guide to the Galaxy trilogy. It's actually the fourth book in the trilogy. And when the dolphins leave Earth in this book, that's what they say. Hey, so long and thanks for all the fish. But we're not talking about fish here. We're talking about PAHs, which are polycyclic aromatic hydrocarbons. And I found this plot of these unpronounceable names, etc. And you can see that there are these carbon things all put together in the chemistry, right? Well, you know them because PAHs are produced when you burn fuel. And so on your grill, when you're cooking your burgers and you get all those black lines on those things, them polycyclic aromatic hydrocarbons, okay? They're good eating, So it's sort of the soot from the grill type thing, all right? And that's what a polycyclic aromatic hydrocarbon is in your life. But to astronomers, polycyclic aromatic hydrocarbons, they can be damn beautiful. That's PAHs in the universe, okay? All right, they actually emit at several bands in the near to the mid-infrared, okay? And this is a picture of the nebula GUM-29, and you are seeing emission from a lot of PAHs here, all right? And this picture in the infrared was, of course, taken by the Spitzer Space Telescope, all right? And Spitzer has had a 16-and-a-half-year career. Unfortunately, it ended last week, okay? So the Spitzer was launched in 2003 and had its primary mission for 6 years. This is called the cold mission in retrospect because it had the coolant to keep certain of its instruments really cold, which is what you need for infrared. When you're looking at heat radiation, your instruments need to be cold so there's not excess heat that interferes with your observations. After the coolant ran out in 2009, 2 instruments that needed coolant were decommissioned, and it went into what's called the warm mission, right? That went on for several years, and it was scheduled to end in 2018, but with delays to the James Webb Space Telescope, they extended it, and it now became the Beyond mission, an extension to 2020, and that is what has just expired. And so Spitzer, as you can see over here, had their idea of, all right, it's the final voyage. All right, there are a lot of Star Trek fans out at the JPL, okay? So this is what they came up with. And so in the Spitzer final voyage, the last observation was on January 28th. Then they started turning off the instruments. And at 2:30 last Friday, or was it last Thursday? Yeah, it was last Thursday. They sent the last command to turn it in, put it in safe mode. And so the Spitzer Space Telescope is still out there. It's on an Earth trailing orbit. It's orbiting around the sun, but it is now in safe mode and will no longer be producing science. So we have had some amazing images from Spitzer, and I just wanted to pay tribute with some of them. This is the star-forming regions in the constellation of Aquila. I mean, just look at the beauty of the dust. I mean, Hubble has some great star-forming region images, but Spitzer's able to tie them all together with all the background gas that we don't see with Hubble. And you can see there's the amazing amount of star formation that's going on in this region. And talk about an even more amazing star formation, what we see in the Large Magellanic Cloud. These are all the star forming regions in the Large Magellanic Cloud, including the Tarantula Nebula right here, the largest star-forming region, not in the Magellanic Cloud, not in the Milky Way galaxy, but in the entire local group. All right, there's so much amazing stuff that Spitzer revealed to us in the Large Magellanic Cloud with this survey. And finally, up on galactic scales, this is the galaxy M81, and what we see in visible light is generally these dark dust lanes in the spiral arms, and look how beautiful it is. Look at all the detail of the dust inside these galaxies. You can really see the spiral arms just jump out. So Spitzer has had a 16-and-a-half-year history of producing some amazing science that is complementary to the other great observatories, Hubble and Chandra. And I've had the privilege of working with some amazing people at IPAC and JPL, and it will be missed. But hopefully the James Webb Space Telescope will be online soon enough, and we'll be able to surpass these and bring them even more. But we bid a fond farewell to Spitzer. All right, time for our featured speaker. And let me just switch PowerPoints. Oops, that's the problem with using that. There we go. Our speaker tonight is Frank Summers from the Space Telescope Science Institute. He has been an outreach astrophysicist here at Space Telescope for, what year is this? 19 years coming up, okay? And he's been your host for the Public Lecture Series for 18 years of that. I usually try to tell you something interesting about myself when I give talks, so I will introduce my wife sitting in the front row here, and we met at the University of California, Berkeley Ballroom Dance Club. So Carolyn and I have met dancing, and we do an absolutely mean West Coast swing. This lady really knows how to do a West Coast swing. All right, and she makes me look good on the dance floor. And sitting next to her is my mom, who taught me how to tap dance when I was 10 years old. So my two dancing partners in the front row. All right, enough about me. Let's talk about some cool things in the universe. All right, the Crab Nebula and things that go kaboom in the night. And we're going to start about this by talking about stars. And one way to think of a star is it's a gravitationally confined nuclear fusion reactor, okay? Now, when you think of nuclear reactors, you're probably thinking of the cooling towers at nuclear power plants, okay? But that's nuclear fission, okay? These power plants create energy by nuclear fission. And fission is when you're breaking atoms apart. And the most popular fuel in fission reactors these days are uranium and plutonium. Specifically, uranium-235, which captures a neutron and then breaks off into two pieces, and the energy that it breaks off into those two pieces is used to heat water, which then drives wheels and creates the power and energy, okay? So this is fission, taking large atoms of 250 neutrons and protons, breaking them apart, okay? That's not what we're talking about. We're talking about nuclear fusion, all right? And nuclear fusion reactors do exist, okay, but they're still in the experimental stage and have been for several decades. All right? And the idea is you're fusing small things together. So take hydrogen, smash it together enough, and then you create helium, okay? The simplest, lightest elements making slightly heavier light elements, okay? And this requires million-degree temperatures, all right? And when you create million-degree temperatures, you're going to create this huge pressure pushing out, right? Okay, so how do you keep all this plasma together? All right, well, what you're looking at right here is a tokamak, okay? This is a tokamak fusion reactor, and it uses what's called magnetic confinement, okay? So you get these really strong magnetic fields to confine the plasma so that you can get it up to these really high temperatures. As a matter of fact, this one, sometime in 2018, was the first one to reach the magic temperature of 15 million degrees. All right? So they're making serious progress. I mean, last time I looked into fusion reactors, they really hadn't barely gotten to the 1,000,000-degree temperature. They're up to 15 million here. They may be even further because I'm not a pure expert in that. And so the idea is really just make sure that you recognize that energy is generated by combining light atoms together. It also is kind of depressing for those of us who grew up in the 80s that we are really a long way from the Mr. Fusion from the Back to the Future movies. Of course, I kind of worry about this because if the temperature gauge on my car goes up to 15 million degrees, okay, that's a serious overheating problem you might have here. All right, so we're not going to have our Mr. Fusion anytime soon, but maybe by like 2030, there's a company in England that predicts by around 2030, they might be able to make it commercially viable to have fusion reaction. I've been told that for many decades, so I'm going to take that with a grain of salt. But hey, cross our fingers, because fusion would be a great way to produce. So if we don't have fusion reactors, that's sustainable fusion reactors on Earth, where are we going to go? We're going to go to the stars, because our sun is hot. It's got a surface temperature of 6,000 Kelvin, and it's very luminous. It produces 4 times 10 to the 3 ergs per second. And most of you don't know what ergs per second means, but you don't need to know. You just need to know it's a really big number, and I'm going to use that later in my talk, okay? All right. If you translate that luminosity into watts, it's 4 times 10 to the 26 watts. All right, you're used to a 100-watt light bulb? Yeah, this is more, okay? Matter of fact, it's so much more, it's really more than the 1.21 gigawatts that were used in the Back to the Future movie, okay? Matter of fact, Marty should reply to him and say, well, that's nothing because the sun is 400 gigawatts, okay? So really, yes, a million billion times larger than the gigawatts, or actually, he always said gigawatts in the movie, and it always bothered me, all right? But, you know, sort of like GIF and GIF, right? All right, and we always say gigawatts these days. Anyways, so with that energy, it's created in the core, where the core temperature is that magical 15 million degrees Kelvin, okay? So that's what makes that tokamak reactor so important, that they reach the magical temperature that is the core of the sun. And at that temperature, and of course the pressure in there, you can create nuclear fusion. Okay? So the nuclear fusion is happening in the core of the sun, and instead of magnetic fields to keep everything together, this is gravitational confinement. So it's the mass of all the outerlying layers pressing in that provides the pressure to keep this all together so you can get the density and the temperature and the pressure necessary for nuclear fusion. All right? So we're going to go into a little bit of detail so that you understand the process. It's not quite as simple as you might think. Okay? So we're going to take a couple protons up here, right? We're going to smash them together and create heavy hydrogen, which is also called deuterium. And that creates some energy in a beta particle and a neutrino going off, okay? Then you add another proton coming in to hit this deuterium, and you can make light helium, helium-3, and that gives off a photon. And then you take 2 of these helium-3s together, smash them, you get a helium-4, which is your stable nucleus of helium, and then you get 2 protons coming out. So the total thing is you get like 6 protons going in, and then 1 helium and 2 protons coming out. All right? Which, if you just get rid of the extra protons, the simple way to remember it is down here, which we usually think of, is 4 hydrogen go to 1 helium plus some energy. Now, where does that energy come from? Okay? And it's really kind of cool when you think about hydrogen fusion to look at exactly how it comes about. So you've got the mass of 4 hydrogen atoms. Together is 6.69 times 10 to the 24th grams, okay? The mass of the helium atom is 6.64 times 10 to the minus 24 grams. And the difference is 5 times 10 to the minus 26 grams, okay? Now, we all know a gram is a pretty pathetic amount of weight, right? Of mass. And 10 to the minus 26th of a gram is really even more pathetic than pathetic, right? But you're going to turn that missing mass into energy. And you can do that via the famous equation E equals mc squared. Did you ever think you'd actually have reason to use E equals mc squared? Most people is like, oh yeah, it's that famous equation. I have no idea what it means, but yeah. But yes, this is where it comes in. Energy equals mass times the speed of light squared, okay? So that missing mass becomes energy, and it produces 5 times 10 to the minus 5 ergs. And as I said, you probably don't know what an erg is. I have there a fun description of what an erg is. It's the amount of energy a flea needs to use to do a push-up. So a flea doing a push-up, but this is 1/100,000th of a flea doing a push-up, okay? So it's a pathetic amount of energy, okay? But when you do the math, that's the pathetic amount of energy from one nuclear reaction, okay? One nuclear fusion reaction. How many of those do you need to produce 4 times 10 to the 33 ergs every second? Okay? You can do the math. There's the math for you. The result is really kind of cool, okay? So, the sun is powered by the conversion of mass to energy at a rate of about 5 million tons every second. Think about that. 5 million tons of mass is converted to energy every single second for our sun to shine. And the sun is just one of a billion stars inside, maybe 100 billion stars in our galaxy. That's an awful lot of mass converting to energy to power the stars in the universe. That's kind of cool. All right. But stars will eat up their mass in the core. If you're burning it at 5 million tons, no, first of all, the star is many, many, many more larger than 5 million tons, okay? But after a few billion years, you can start to make a dent in there, okay? So stars, like the sun, they will end not with a bang, but a whimper. Okay, so in the core, you've got hydrogen converting to helium, okay? And this is the main sequence lifetime of a star. It's the stable one. Our sun will be in this for about 10 billion years, 9, 10 billion years, okay? This is when stars are at their most stable, hydrogen converting to helium. But eventually, they're going to build up a whole bunch of helium in their core that will not undergo fusion at 10 million degrees or 15 million degrees. It has to have a much higher temperature. So the hydrogen to helium moves out into what we call shell fusion, okay? There's a shell around an inert core of helium, and that shell is converting hydrogen to helium, okay? And then when you heat up to about 100 million degrees in the core, okay, it contracts and heats up, then helium can use what's called the triple alpha process to become carbon. So 3 heliums together, you get 1 carbon out. 4 plus 4 plus 4 is 12, right? To get the helium to the carbon, all right? And that's when the star hits 100 million degrees, and this produces another semi-stable phase of the star. It's called the red giant phase. And red giant means that because of this excess energy and the heat provided by it, we go from the sun being this size to the red giant being that size. The sun will bloat by a factor of 100. Okay, we'll go from a what's called a yellow star to a red star that is 100 times larger. Mercury and Venus will be swallowed by the sun when this happens. This will happen. Let's see. The sun's about 5 billion years old. Somewhere between 10 and 12 billion years is when this will happen. So we got 5 to 7 billion years left. Okay. Now, actually, the sun is heating up during that process, and Earth will only be livable for another 3 billion years or so. Okay, so it's not quite as long as that. But the red giant phase will kick in 5 to 7 billion years. And then after the red giant phase, you end up with the helium shell fusion, okay? You build up carbon in the core, All right, it's not hot enough to fuse carbon into the next element, and you get the helium shell fusion, helium turning to carbon, hydrogen turning to helium. You get these shells. That's as far as our sun will go. That's as far as a medium mass star will go. They do not have enough gravitational pressure to heat things up to go beyond 100 million degrees into the next stage where you get carbon fusion. So they'll build up carbon and build up carbon and build up carbon, and they won't get past it. At that time, you suffer what's called a helium catastrophe, when everything's trying to burn, not making the fusion, and it blows off its outer layers. And this is what we call a planetary nebula. So this is in the center, right here. That's the core of the star, and out here is the material of the atmosphere of the star blowing off into outer space. Why is it called a planetary nebula? Because astronomers were ignorant when they first called it this, okay? They didn't know what it was. They said, it looks kind of like a planet, right? And you can sort of imagine them thinking this looks like a planet. But this is actually the death of a medium mass star. And they can be stunningly beautiful, okay? Sometimes we call them cosmic butterflies. Here is one that's got a dust disk around the star, and so it goes off in two directions. This one's called the Bug Nebula, but we did a press release on it where we said it looked like a butterfly, and so everybody's calling it the Butterfly Nebula now. We renamed this object via press release. Unintentional, but hey, that's the power of Hubble for you, okay? And here is another one called the Ring Nebula, okay? And you can see just these wonderful, beautiful things of material being thrown off. And then right there at the core, right there in the core is that stellar remnant, the remains of the star. And that is called a white dwarf. It's the remains of this medium mass star. It's basically that carbon core, okay? So in the process that it's trying to, go up to carbon fusion and does not quite getting there, it burns everything into carbon and blows off the outer stuff around it. So it is no longer producing energy. It's a really hot carbon core. It's massively hot. It's dense, and it slowly cools. And this is a white dwarf. This right here, that's the star Sirius. That's Sirius A. It has a companion star, Sirius B, that is a white dwarf. So this is a main sequence star. This is a white dwarf, okay? And the easiest way to remember what a white dwarf is, it's a giant glowing piece of carbon. So it's a cosmic charcoal briquette, all right? And you could do an awful lot of marshmallows off of a white dwarf star because it will slowly cool for billions, tens of billions of years, okay? But these are not the subject of what we're talking about tonight. What we're really talking about tonight are the things that go kaboom in the night. And so how do we get to that kaboom? Well, we left off here where we've got the carbon in the core and helium shell fusion, and hydrogen shell fusion. Well, if you have more mass, you can compress that, and then the carbon goes to oxygen. And you can do this over and over and over again with these really massive stars. So you have carbon going to oxygen, oxygen going to neon, neon to magnesium, magnesium to silicon, silicon to iron, and we get an iron core, okay? And this causes the star to swell up even further to become a supergiant star. And the supergiant star we all love best is Betelgeuse. This isn't a picture of it, a picture that resolves the pixels of Betelgeuse. And you can see the size of the star here, right? All right, the size of the star here. This, in comparison, is the size of Earth's orbit. And this is the size of Jupiter's orbit. So if Betelgeuse were in the place of the sun, Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter would all be orbiting inside the star. They'd all be swallowed by the star, okay? That's how big a supergiant star is, up to 1,000 or a couple thousand times the size of our sun. So we get these supergiant stars. But there's a problem with these stars, that you cannot fuse iron to a heavier element and get out energy, okay? That's exothermic. You take things, put them together, you get energy out, exothermic. Combining iron to make heavier elements is endothermic. It eats up energy. So you cannot go beyond here. And you build up iron, and you build up iron, and you build up iron in the core until you reach the Chandrasekhar mass of iron, at which time the nuclear structure collapses. It breaks down on the nuclear scale. Electrons combine with protons to form neutrons, releases a flood of neutrinos, and the star blows itself apart. Okay? This is the kaboom. All right? The star blows itself apart in a supernova explosion. It releases 10 to the 51 ergs. All right, we talked about the sun producing 10 to the 33 ergs every second. If you integrate that over the entire lifetime of the sun, you almost get 10 to the 51. In a millisecond, as much energy as the sun will ever produce is released in an explosion. That's a serious explosion, okay? They are cosmic beacons. Here we have a picture of a galaxy. This galaxy over here is, 100 million light years away. But what can we see? We can see what looks like a single star. And normally we'd say, oh, that's a star in our own galaxy. But that's not. That's a supernova explosion in that galaxy. 10 to the 51 ergs is as bright as 1 billion stars. So we can see these supernovae across billions of light year of space. And what they do is a sort of form of galactic recycling, because the gas collapses to form stars, and the explosions blow that gas right back out into space. But it's not the same gas because it has been enriched. All those elements that were formed in the supernova and more that were formed during the explosion. So as the main sequence forms all these elements in the core, and then the supernova blows them out and actually creates, because you got a lot of extra energy during the supernova, you can actually use those endothermic reactions to make larger and larger elements. You blow them out into space. So where do these elements come from? This is a cool chart that shows you the cosmological sources, the astronomical sources of the elements in the periodic table. And what we're going to pay attention to is down here in the lower right, the exploding massive stars, and you can also explode white dwarfs. These are your supernova, your green and your light blue, right? And so you can see, everyone take a deep breath. You breathed in oxygen. Where did that oxygen come from? It did not come from the Big Bang. Hydrogen and helium only came from the Big Bang. That oxygen you just breathed in came from a supernova. If you look over here at oxygen, right up here, it's green. It comes from the explosion of massive stars. Whoa, kind of cool, right? All right, you can do more than that. You like to put salt on things? Well, here's your sodium over here, right? And here's your chlorine over here. Sodium chloride is salt. Where did it come from? Supernova explosions, okay? When you were watching the Super Bowl, eating those salty snacks, you didn't realize you were eating supernova dust at that time, okay? All right. So many of the elements, the calcium in our teeth, the iron in our blood, come from supernovae, okay? Our connection is not to the stars, but really that we come from the stars, which is kind of cool. All right. But again, that's not the story that we're trying to tell here tonight. We're trying to get beyond that. Let's talk about the remnants. What's left over after these supernova explosions? In the core, when you have a high mass star, 8 to about 15 solar masses, you end up forming a neutron star at the core. Remember I talked about the protons and the electrons combining to form neutrons, all right? And that's what happens when the nuclear structure collapses. Well, you build up this huge ball of neutrons, all right? And for not too massive stars, you create this giant core that is basically a ball of neutrons, okay? Neutrons packed at atomic density. So this is a star, a mass of material at basically at the density of an atomic nucleus. Do you know how to get the density of a neutron star? You start with a herd of 50 million elephants. And you take all those 50 million elephants and pack them into a thimble. 50 million elephants in a thimble, that's the density of a neutron star, okay? The other thing, because you got the mass of a sun in basically a 10-kilometer radius, all right? And when you collapse things down, they tend to spin up, all right? And neutron stars can create what are called pulsars. So this is a diagram over here on the right. This diagram is of the pulsar. There's the neutron star in the core. Here are the magnetic fields going around it, and the magnetic fields can fling off emission, basically electrons and such, along a beam. And so if you've got this thing spinning, and it goes, like, you can see that it's not on axis, so it's going to spin like this, right? And you're going to see a flash of light, and then it comes back here with a flash of light, and a flash of light, and a flash of light. Every time it spins, you'll get a flash of light. Okay, these are cosmic lighthouses. All right, and they're called pulsars because we see this pulsed emission. Right? They can spin 30 times a second, 100 times a second, sometimes, once every 3 seconds. But you've got these things that are 10 kilometers across spinning at these incredible rates. All right, and we've actually watched them slow down over the years. This is important. It will come back later in the talk. If you have a really high mass star, you collapse through the neutron star phase and you go into becoming a black hole. This is the ultimate density that we've got, okay? It's black. What does that really mean? It means that there's no emission from it, okay? The escape velocity from the Schwarzschild radius of a black hole is equal to the speed of light. So light that tries to leave that black hole comes back onto it, okay? Light cannot escape from inside the Schwarzschild radius, okay? That's why it is black, okay? And that means that the black hole itself is not directly observable. Because what are you going to observe? There's no emission coming from it. Now, yes, there could be Hawking radiation. That's another talk, okay? So we have to do indirect observation, all right? And the most common way we see black holes is by the X-ray binaries. So this is a diagram here of an X-ray binary. This is a black hole in here, and you have a star that's orbiting around it, and the material being pulled off that star flowing into a disk around the black hole, and then some of the material being thrown off. Some of the material goes into the black hole. The magnetic fields, again, spinning around, throw things off in jets. All right, so you can see the jet emission. These are visible in X-rays. All right, and there were a tremendous number of X-ray dots out there, X-ray stars, until we figured out, okay, these must be black holes in X-ray binary systems. They're also called cataclysmic binaries, which I think is a cool name, okay? Cataclysmic binaries. Whoops, sorry, let's go back. Oh, there we go. And so with the X-ray binaries, you got accretion disk and jets that you can see. The other way to tell whether the black holes exist are their gravitational effects, gravitational lensing, or the effect for supermassive black holes for stellar orbits around them, etc. So we cannot see these directly, all right? So now we get to the meat of the subject for tonight, and it is live fast, die young, and leave a good-looking corpse. Because I didn't talk about the timescales of those fusion processes. Now, if you naively think about it, we got a 1 solar mass star, and we've got a 10 solar mass star. This has 10 times the amount of nuclear fuel for the processes going on. So which one would you expect to live longer? The one with more fuel, right? That's what you would normally think. And you would be totally wrong, because the more massive stars heat up to higher temperatures and therefore burn through their nuclear fuel at a much higher rate. So that 1 solar mass star, according to this chart, you can say, okay, here, 1 solar mass goes up to about 10 to the 10th years, 10 billion years for its lifetime. All right? Whereas that 10 solar mass star right here goes up to about 20, 30 million years. Okay? It has 10 times the nuclear fuel, but it lives for less than 1% of the time. Whoa, that's burning, that's living fast and dying young, okay? And do they leave a good-looking corpse? Oh, you betcha. They create some beautiful nebulae. This is one of my favorites, Cassiopeia A, and this is observed in radio light from the Very Large Array. Okay, so you're seeing electrons spiraling around magnetic field lines emitting in the radio. We can also see, it doesn't look just good in the radio, we can also see it in the infrared from Spitzer. You can see all the dust and light that's heated up in here. We can see it in Hubble, in visible light, where we can see the fine filamentary structure of this shell of material that has been blown out into space. But they look even better in X-rays, because you have such high temperature gas, you can see all the material inside this bubble, this expanding bubble of material that's been blown out into space. This is the guts of a star bursting across interstellar space. All right? Stars blow their guts out right at the end of their lives, okay? The massive ones at least, okay? And X-ray is the really cool place to see it. That is Cassiopeia A. Here's the X-rays of Kepler's supernova remnant that was observed by Johannes Kepler, I think 1604, I believe. And then also his predecessor, Tycho Brahe, he also got a supernova named after him. Tycho's supernova remnant, again, in X-rays from Chandra. All right, and you can see these big giant bubbles of material spewed out into the universe. Now, Hubble doesn't quite see all the details, but it does have a couple pretty ones. In the Large Magellanic Cloud, here's one called N49, and you can see that delicate filamentary structure. Okay, because Hubble's only observing things at thousands of degrees, not at millions of degrees. So it only gets the edges of it, and it really gets the edges of one that we call the red bubble, a supernova remnant 0509-67.5. Needs a better name, so we call it the red bubble from Hubble, okay? So we look at these supernova remnants, okay? And you can see them all have these roughly spherical structures. Well, not all of them do. But this is the blast wave driven supernova remnant, where you can imagine if you have a point explosion and it blows off in all directions, you're going to get this beautiful bubble, okay? And it's just amazing sort of stuff of how these stars end their lives and spew the elements out into interstellar space. But I'm here to tell you a tale of two supernovae, okay? And this is why I gave out supernova 1006. So the lithograph we gave out tonight, supernova remnant 1006, this is the visible light from Hubble. Now, it's a tiny little filament. I talked about seeing only the edges of it. This is actually a tiny piece of the edge of 1006. Here is the X-ray view of it, okay? And that yellow square up there is approximately what Hubble sees in the right-hand image, okay? So you can see this giant bubble here. And so we've got 1006, and we're going to contrast it against another supernova remnant. Both of these supernovae were observed by Chinese astronomers. That's how we can date when they happened, okay? There wasn't European astronomers doing stuff in the year 1006, but Chinese astronomers observed this, and we were able to date it. And 50 years later, they saw supernova 1054, okay? Some of you may recognize this as the Crab Nebula, okay? And so we have 1006, we have 1054, two supernova that were observed, that formed 1,000 years ago. But they don't really look alike, do they? All right, this one has this beautiful bubble shape, And the Crab Nebula sort of has like a football shape. It's not really spherical. And this has got, filamentary structure around the edge, but nothing across the center. And this one has filamentary structure across the whole thing. Now, that's kind of weird, isn't that? Okay, well, it's not that the filamentary structure is weird, okay? Because we do see filamentary structure. And this is filamentary structure in Cassiopeia A, and you see the gorgeous structures. These are actually Rayleigh-Taylor instabilities, okay? When you get the pressure differential and you create these gorgeous filamentary things. Rayleigh-Taylor instabilities, look them up. They're a lot of fun. But this has all this filamentary structure as part of this big bubble structure, okay? So it has some of that, but it really has the big bubble structure as its dominant. So what's going on here that these two, which are both 1,000 years old, don't look anything alike each other? Well, the answer is that I'm hiding something from you, okay? I'm not lying to you, but I haven't given you the full piece of information. Because these two are not being seen at the same scale, right? They're roughly actually at the same distance. But if Hubble can take that image with one pointing for the Crab Nebula, okay, it does this whole thing in one pointing, and on 1006 it only did one pointing of a small region up here, says something's different. So if I put these at the same physical scale, 1006 is about 60 light years across, and the Crab Nebula is 10 light years across. Whoa. Okay, so this is what smacks you as an astronomer that you've been talking about the Crab Nebula as a supernova explosion, and you knew it was not quite the same as all the others, but you sort of said, okay, well, it's got to have mostly the characteristics of a blast wave supernova, but it doesn't. This is this one on the left is a blast wave dominated supernova remnant. The Crab Nebula is clearly not a blast wave dominated supernova remnant. What the heck is it? It is a pulsar wind nebula, okay? And this is where things get really cool. Okay, so here is our view from Hubble of the Crab Nebula, right? But to really understand the Crab Nebula, you want to use multi-wavelength. You don't want to use just visible light. You want to use all the wavelengths you have at your disposal. So here is a separation at the same scale of radio, infrared, optical, ultraviolet, and X-ray views of the Crab Nebula, including a composite image in the lower right, okay? And we're going to work from the inside out. Let's start with the X-ray. Here is a comparison of the Chandra X-ray image versus the Hubble visible light image. And the Crab collapsed to form, the Crab supernova collapsed to form a neutron star. A neutron star that spins, has a pulsar. The Crab pulsar is seen clearly in X-rays right there at the center of the Crab Nebula. It is a 33 millisecond pulsar. It spins 30 times a second. All right, so take all of Baltimore City and spin it 30 times a second. All right? And actually, you'd have to have Baltimore City the size with the mass of the sun in Baltimore City and spin it 30 times. That's a tremendous amount of energy, okay? And all those magnetic fields are spinning around, getting wrapped up, and the material's shooting out as jets. And here's the jet that you see in X-rays, spewing out from that pulsar. And there would, of course, be another jet coming off across here. If you really process it, you might be able to see a little bit of that jet, but it's not easily visible. Plus, there is a disk of material, a ringed disk of material. See that ring here and see that ring here? It's more of a torus type thing. You've got a disk of material around it. And if we take time-lapse things, we can actually see energy propagating out. So with these magnetic fields getting all wrapped up, all right, and forming up, it's an efficient energy distribution system. Energy flows away from that pulsar. The pulsar is creating huge energy that's flowing out into the system. What's it going to heat? Well, it's going to hit the gas around it, all right? And so here we have two images. This is Spitzer infrared image here, all right? And over here is Hubble, invisible light in a medium band of visible, green, okay? And you see all this blue gas on the left. That blue gas is the gas that has been heated by this pulsar emission and is now emitting what's called synchrotron radiation. All right? Synchrotron radiation is when electrons spiral around magnetic field lines and emit radiation. Okay? And the tighter they spin around it, the higher energy radiation they hit. Synchrotron radiation from the Crab is seen in radio, it's seen in infrared, it's seen in visible, it's seen in ultraviolet, it's even seen a little bit in X-rays. You've got tremendous amounts of synchrotron radiation. And you want to convince yourself that it's coming from the magnetic field lines, you look at this Hubble image and you can see the linear features. Look at this structure here, and you get the emission following all of these very striated lines in here. So you've got this synchrotron radiation from the material, and it's at many different energies, from low energy radio to high energy ultraviolet and X-ray. That energy then goes out and hits the blast wave, okay? So this is what we see in visible light with Hubble. We see the elements that are spewed out from the supernova being energized by that synchrotron radiation, okay? The energy here is not due to the energy of the blast wave, it's the energy that's coming from the synchrotron radiation that heats it up, and that's what we see with Hubble in oxygen and in sulfur. So we have this Russian doll structure in the Crab Nebula. You have the pulsar, which you can see beautifully in X-ray, creating all this energy, which then heats up the gas that emits in synchrotron radiation, and that synchrotron radiation then hitting the elements that glow in visible light. One of the experts I worked with on this project says to me, well, look, we think of these supernova remnants as glowing on their own, but without the Crab pulsar, we probably wouldn't even see the Crab Nebula. This is a pulsar wind nebula. The energy, the wind from the pulsar, driving all of the emission that you see in X-ray, infrared, and visible. That's a cool story. And that's the story we wanted to tell in our latest 3D visualization. So our visualization is Crab Nebula, the multi-wavelength structure of a pulsar wind nebula. When I say we, who are we? We are NASA's universe of learning. This is the outreach funding from NASA that used to be on a mission specific. It used to be just Hubble did its outreach, and then Spitzer did its outreach, and Chandra did its outreach, and so on. They combined it into in a program that works across wavelength, and it's all about getting the stories out, regardless of the wavelength. So we combine the Space Telescope Science Institute, we're the home of Hubble, with Caltech IPAC, the home of Spitzer, with the Center for Astrophysics, Harvard and Smithsonian, the home of the Chandra X-ray Observatory, JPL, NASA JPL, and Sonoma State University. All of these groups working together. So we've got Hubble, Chandra, and Spitzer all working together to do this project, okay? And this is the combined image that we released as part of this project. It has, you can see the X-ray pulsar in the core, it has the red of the infrared from Spitzer around that, and then it has the yellow of Hubble in the oxygen emission around that. So I'm going to talk a little bit about how we did the visualization, because, hey, that's my specialty. If you remember from last year, I gave a talk where I talked about an astrophysicist. That's me. That's my moniker for myself as an astronomer who does visualizations, an astrophysicist. So the X-ray for the Crab Nebula. Well, we just want to get across the idea that there's the pulsar, the disk, and the jets. And these are relatively straightforward geometries to do in 3D, okay? When you're thinking of 3D modeling, all right, creating a disk, Yeah, it's pretty straightforward. Creating a sphere for the pulsar, great. Making the jets was a little more work on this, but we have some really good artists here who go out and were able to create the jet, and then we got this nice fuzzy haze around it to work in the X-rays. So I don't want to diminish the work that Joe did on this, but this is more standard 3D stuff because you can actually have physical stuff. But then you go to the synchrotron radiation, which we're representing with Spitzer's observations in the infrared. And this is much more of an amorphous cloud. Plus, we have to get across the idea that it's the magnetic field lines from which this radiation is emitting. So Joe also did this one, and he chose to do it via something called fluids. And basically, as you can see here, this is just drawing lots of squiggly lines in 3D, okay? Now, this is the later version of the model. The first version of the model was just to try and create the three-dimensional structure, and then it looked like a layer cake type thing, and you're trying to get the rough shape of it. Now, do we know what it looks like when we spin it? No. But that's why you have me on the project, who, as the astronomer, who's able to sit there and say, all right, well, it's roughly going to look like this. And you can see, for example, this gap right here. See that gap right there? That's actually a magnetic torus. It's a belt that's squeezing in, all right? And there's no synchrotron radiation for this belt around there, all right? And I'm around to sit there and talk to the experts and make sure that we put as many astrophysical features into this three-dimensional model, this approximation of what's going on. And then when you take all these squiggly lines and then emit fluids from it and visualize it, you can get that, all right? And it's hard to believe that that could come from that. And that's not the final version of it. That's still, one of the medium, halfway through to create this. But you also see that by doing it with these squiggly lines, we get the feeling that it's the magnetic field lines that are creating the emission of it. Now, the hard part came when we tried to do the visible light. And this, I thought, was actually going to be easy because we have some observations, right? We have observations, and these come in the form of velocity slices of the nebula, all right? So these images are oxygen-3 observations, and you use a very narrowband filter that you can adjust back and forth to pull out the Doppler-shifted emission, okay? So at the distance of the Crab Nebula, there is a certain emission line of oxygen, oxygen-3, that occurs at a certain wavelength. But if it's moving toward you, then that emission is going to be blue-shifted to shorter wavelengths. And if it's moving away from you, it's going to be red-shifted to longer wavelengths. So the stuff on the front of the nebula that's moving toward you, blue-shifted, should be at shorter wavelengths. And the stuff on the back of the nebula that's moving away from you should be red-shifted to longer wavelengths. And if you use a filter to pull out those different Doppler-shifted velocity slices, you get this. And so working from the back to the front, you can see the top left working through to the bottom right, which is the stuff in the front. And you sort of get these velocity slices through the nebula, from which we had expected we'd be able to create an interesting 3D model. We were wrong, okay? Translating from velocity space to real space doesn't have a really good solution, right? You've got velocity stuff moving outward, that gets very fuzzy. So the paper that this came from did their own version of it, and this is sort of the rotation of their model, and you can see it particularly here. Look at the blobbiness of that, okay? All right, and we thought that there was some new data that would be able to help us, and yeah, no, it didn't help us. Matter of fact, there is some new data that won't be coming out till this year that maybe, I still don't think it will actually help us, okay? The translation from velocity space to real space was much more difficult than we thought it would be. So what are we going to do? Well, we're going to go back to Copernicus, okay? So we invoke the Copernican principle. All right, what is the Copernican principle? Well, Copernicus, as you know, was the one who promulgated the sun-centered solar system instead of the Earth-centered solar system, the heliocentric model versus the geocentric model, okay? And what Copernicus did is he said, hey, we're here on Earth. We're not at the center of the solar system. And we astronomers have called this into a Copernican principle because we learned, later that, hey, you know what? The sun is not at the center of the galaxy. And we can go even further to say that our galaxy is not at the center of the universe. We are not at the center of anything, okay? That's the Copernican principle. We exist at no special point in the universe, all right? And so therefore, the crabby Copernican principle is to say that we have no special view of the Crab Nebula, right? So we see all these filamentary structures across the face, and we see all this splay of material around the edges. But if I looked at, that's because we're looking at it from here. But if I look at it from the side, I should probably see the same thing. Filaments across the face, splays of material around the edges. So, using the Fabry-Perot data, I was able to pick out which filaments we thought were on the front of the nebula and which filaments were on the back. We could then go into the Hubble data, which is much higher resolution than this, pick out those filaments and paint them onto basically a potato, okay, that had the filaments on the front, filaments on the back, and we could connect them across the edges so that we had filaments from every direction, okay? So we got the image on the right is the filament potato that has filaments, and as you spin it, you'll see filaments from every direction. So what are we going to do about the splays? Now that we have those filaments, we have to add in some splays around it, okay? And to do this right took a long, well, actually it's impossible, okay, according to my team. To do it really, really right, because you don't know how thick those splays are and everything, so we cheated, okay? We did not do a full 3D model of these splays. We actually did 18 2D models of these splays. So we've got a plane of material here that creates the splays. And then you rotate that 10 degrees and do another splay material. And 10 degrees, another set of splays. And you do 18 of these, and you fill out a full rotation of splays. So that as you're watching that potato spin here and you're seeing all the filaments, from every direction you're seeing splays around it, okay? So this isn't a full 3D model, it's a 2.5D model. All right? And if I were trying to fool you, I wouldn't admit to what we had to do to get this to work. But this is what we had to do in order to get that three-dimensional structure. So this model only works from that one camera path that we have in the movie that you're about to see. All right? And it shows you that really getting that filamentary, beautiful structure is really difficult, all right? Matter of fact, I was talking to my visualization friends out at JPL, all right, and he was like, I knew you couldn't do that, all right? And he was like, yeah, I sort of thought I could, but, we have not figured it out. Maybe we'll be able to figure it out. The only way to do this and make it self-consistent and really look good is actually to do a simulation of this type of stuff, but then it wouldn't match the Hubble image very well. All right, and so it was the tearing back and forth between wanting to make it look like the Hubble image and wanting to make it have this beautiful structure, and this was our approximation. So, can we take the lights down? I got this big light here because I'm about to show the movie. Thank you, Calvin. All right, so here we go. Crab Nebula, the multi-wavelength structure of a pulsar wind nebula. Where's my cursor? Oh, I had to pull the cursor back onto my screen. All right, so some final thoughts for you. What you might take away from this talk tonight. The universe is powered by nuclear fusion. The elements, including what you're made of, were forged in the stars. But those stars, they do not last forever. And the stellar graveyard of the universe is filled with these white dwarfs, these neutron stars, and these black holes. But before they go ungentle into that good night, they rage against the dying of light by putting off these gaseous dust masks of planetary nebulae and supernova remnants. And finally, that Crab Nebula, pictured on the right there, is not the prototypical supernova remnant we once thought it was. It is a pulsar wind nebula. It is unusual. And if you enjoyed the visualization, you can watch it on the Hubble Space Telescope channel on YouTube. And if you would like to download it and show it to your friends or your colleagues or your dog, you can download it on hubblesite.org. Thank you very much for your attention tonight. Okay, if you have to leave, please go on ahead. But as always, we have Grant with the throwing microphone. All right, so he needs his energy, so please have a question so Grant can throw the microphone. Over there.
There are a couple good ones online as well.
Oh, there are a couple. I can't monitor the chat while I'm talking.
Okay, interesting. So you talked about modeling the invisible wavelength when you did the 3D model. You talked about modeling the filaments and the splay.
I call them splays because they're displays of material, but
are they actually different physical phenomena?
No.
Okay,
What makes it really difficult is that the splays seen edge on are the filaments. Okay. And to get a proper three-dimensional structure, three-dimensional depth to a splay and make it look like a filament was what the problem that I couldn't solve. That's when we went to the 2.5D solution of it in what we were doing. And that's what my colleagues said, yeah, you weren't going to be able to do that, dude. Who do you think you are? And I was like, well, I hoped. So yeah, so really, when you see the filaments across the face, they're probably projected out into you, and they are these splays with their various filaments, their various width to them. Yes, behind you.
It seems like a supernova is a pretty dangerous thing to have go off nearby.
Yeah, I wouldn't want to have one in my backyard. Yeah.
Just what's like a safe distance? Or what's a dangerous distance?
So if you're Mr. Fusion that blows up, how far away do you need to be, right? Interesting thing is that there have been supernovae in our galaxy that probably have affected the solar system. Right?
The Crab Nebula?
The Crab Nebula, well, it was 1,000 years ago, okay, and it's about 7,000 light years away. So I think we were kind of safe from that, but if it were 1,000 light years away, the high energy radiation could do some damage. And there have been papers written on this. What is the safe zone away from it? 7,000 light years sounds like that's enough distance.
How far away is Betelgeuse?
Betelgeuse is about 1,600, if I remember. I don't keep all these things in my head, but I mean, it's much closer. So Betelgeuse, when it goes supernova, might be problematic, but it might not.
That answered two of the questions online, but another is
Yes.
the distance to Betelgeuse we're not quite sure of. There's a plus or minus. And
Of course.
That being the case, how can we tell how old it is?
Okay. So a red supergiant of that mass, looking at the spectral type of it and everything, is only going to live for at most 20, 30 million years. Do we know how many million years it has left? No. But we know how long, from the modeling, how long it takes to progress from the main sequence massive star to the red giant to the red supergiant on that. So this is why we can't tell with any certainty when Betelgeuse will explode. And so the next few million years is the best approximation we can come up with.
Yeah, my question is, what about the magnetars? How come they're not listed there in the stellar graveyard?
Magnetars are not included in this talk. That's getting a little too detailed of the neutron stars that end up becoming magnetars. I'm not an expert on those as well. I did almost an hour just using this stuff, so I'll try and pull in an expert who can talk about those things as well. Okay? Yes.
On the periodic table that showed the sources of the elements.
Yep.
there's
Isn't that, by the way, a cool diagram?
Really cool.
Some astronomers created that over the last 2 years, and it was just like, oh, this is really a lot of fun. But anyways, yes, go ahead.
I was wondering why 2 of them were gray.
2 of them were gray because they're radioactive sources that don't exist for very long and don't therefore come from astronomy. You'll also notice that periodic table didn't include all of the ones that were only created in particle physics experiments here on Earth. Okay, so basically to complete, to make it complete, they did all of the up to the highest element that's created an astronomical source, and 2 of the ones that are smaller are not created by astronomical sources. They're okay.
All right, this is going to be fun. I believe in you.
Uh-oh. Is that a mic drop?
This, this swarms, yeah. Crab Nebula is in the constellation Taurus,
Yes.
and it's labeled M1, Messier 1.
Yes.
And if it were clear tonight, you could see it with a telescope across the street quite easily.
Absolutely.
It would look kind of like a cotton ball, something like that. Or, you know,
And it wouldn't be as colorful as the Hubble image because the Hubble images are narrowband filters designed to pull out those sulfur and oxygen and then give in colors, yes.
yeah, that would, we'd have what we call a white light image through the telescope.
Yeah. Actually, that's a really important thing. This being what, February? Orion is nice and high in the evening, okay? So you get to see Betelgeuse dimming, catch it while you still can. Rigel, Orion's belt, the Orion Nebula, and then up to the right from that is where the Crab Nebula is in the constellation of Taurus, okay? So thank you, Herman. Any other questions?
Check online.
Check online, okay? Let me actually, extrasolar planets next month, right? Yeah.
What is the lower mass limit for a star that can go supernova, and what class of star is it with that lower mass limit?
Okay, so the mass limit for going supernova to form a neutron star is 8 solar masses, and then it's somewhere between 15 and 20 to form a black hole. It used to be 20, but I thought they lowered it, and didn't keep up with that. And these would be O and B stars, basically O stars, the most massive stars and the brightest stars that we have. When we think of massive stars, we think of O and B stars, but the ones that are going to supernova are the O stars and the massive O stars. Okay? Anything more?
Yes, one more.
One more. And we have a question from the audience here, too.
Okay. When a massive star tries to fuse its iron into a heavier element, does it actually succeed in producing it?
It doesn't, well, I mean, it can go a little bit, but then it eats up the energy, so that cools, by eating up the energy that cools it off. So if that fusion reaction goes, it only goes for a short amount of time and then pulls back. And can go for a short amount of time and pull back. So you could, the excess energy provide that fusion, but it wouldn't last very long. So a negligible amount of that happens. But when the star explodes as a supernova, there's plenty of extra energy, and you can then actually power those fusion reactions. All right, last question, because we're getting towards 9:30, and I always have to cut myself off.
Related to the previous question, is all the extra energy that comes out of it is essentially still the conversion of matter to energy? Is that essentially the dynamic?
I'm not exact. When you combine protons and electrons to make neutrons, There's probably something, but there's also the flood of neutrinos that's released as well at that time in that. So there's going to be some of that, and there's going to be some of just the amazing number of neutrinos you create with that. I'm not a particle physicist, so I know it enough to explain the basics, but I'm happy to admit my ignorance on on some of the details.
Subject for a future talk.
Yes, get particle physicists to do all those diagrams for an hour. Yeah, that'll. All right. Next month, Nestor Espinozo will be talking about exoplanets. You know you're not going to want to miss it. That's the first Tuesday in March. The construction will still be going on. Thank everybody who helped produce this, and have a good night.